Hello guys, in this video we are going to see how can we get the camera matrix from the fundamental matrix. So in the previous video we have seen that there is this projective ambiguity that is associated with the fundamental matrix F. So given a fundamental matrix F, there is no one pair of P and P dash that can give you the required solution. There are many different P and P dashes that you can get which will satisfy this fundamental matrix. So given one unique fundamental matrix, there are different combinations of P and P dash that can give you a, a, a result that is satisfying, but that would not be the true result. So that is what we have seen in the previous video. So one can find out that this is something that this at this stage we cannot deal with. So at this stage we are bound to get some reconstruction, that is some camera matrix P and P dash that will give some reconstruction, but in the next stage, that is when we will actually reconstruct the given object from the camera matrices and the fundamental matrix. At that time we will see how can we modify those reconstructions and get close to the true reconstruction. So for now we are just going to find out a pair of P and P dash that satisfies this fundamental matrix. So that's the goal of a video. We are going to find out one possible P and P dash which can be some transformation of the original scene, but that's okay for now. So we are just going to find out one possible solution of this fundamental matrix F. So let's see that. Right, so we have this constraint, epipolar constraint with us. Now what we can do is, instead of this x dash over here, so this x dash can be written as nothing but the capital X projected on to this camera. So we can write this as P dash X. So because this is transpose, so hence it is X transpose P dash. So that is for this X dash. Similarly for this X we can write this as, this X is nothing but this capital X projected on this camera. So hence it is Px. So that is what we have written here. So now it turns out that this matrix that is formed over here, this matrix has to be a skew symmetric matrix, because there is this X transpose over here. So X transpose this matrix and again there is X, and this equals to 0. So if there is a case like this, then this matrix that is over here, P dash transpose FP, this has to be a skew symmetric matrix. Why? Let us see that. So a small proof for that. So if you have any value over here, any vector x, y, z, w, so we are using homogeneous coordinate system, hence there is x, y, z and a w sitting over here. So you can have any vector over here and the same vector will come over here, and there is this matrix over here. So when you multiply this matrix over here, you get this equation over here which is equal to 0. So you'll see that when you compare both the sides, right and left sides, you'll see that since there is only one x square term over here, this has to be 0. So there is no option for a11, a22, a33, a44. They have to be 0 because the right hand side is 0. And the other thing is, now you have two terms, like terms over here, xy, and there is this xy. So you can say keep this as a12 and you can keep this as minus a12. So that will cancel each other and again give you 0. So like this I have just colored the different like terms together so that you will understand that. And when you get that kind of a substitution, you'll see that this matrix is formed, which is a skew symmetric matrix. So you can see that a matrix of this form having diagonal 0 and this is just minus of each other, so that is what is a skew symmetric matrix. So hence we understand that a matrix of equation of this form is only possible if this is a skew symmetric matrix. So that's what we have here. So hence this matrix has to be skew symmetric. So hence if P dash and P belong to this fundamental matrix, then they should be, then this product should be a skew symmetric matrix. That is the first result that we have. So we are going to find out this P dash and P from this result that we have. Okay, so we are going to use the canonical form. So we know that we can keep one camera matrix as I0. So we are done with one camera matrix P, that is I0. So if we set this as I0, then we will have to set P dash like this. So where S is some skew symmetric matrix such that this whole matrix is a matrix of rank 3, because P dash is a camera matrix and it has to be a rank 3 matrix. So S can be any skew symmetric matrix such that this matrix so formed is a matrix of rank 3. Also this E dash over here is nothing but the epipole over here, this point over here, the vector representing this epipole over here, this is nothing but the E dash. Okay, so one can quickly verify this. So given these two matrices, so P is I0 and P dash is this thing, let us see whether this matrix that we have, whether is it a skew symmetric matrix or not. Because if this turns out to be a skew symmetric matrix, then we can say that P and P dash are one possible solution of the camera matrix for this fundamental matrix F. So we'll just substitute these things in this formula. So we have P dash transpose, so this is P dash, so just taking the transpose of it. Also please take into consideration the size of the matrix. So P dash and P both are 3 cross 4 matrices. So if you take its transform, it will be 4 cross 3. So please understand this notation. Over here, this is a matrix. So F is a 3 cross 3 matrix, S is a 3 cross 3 matrix. So both of their multiplication is also 3 cross 3 matrix. So this is a 3 cross 3 matrix and this is a 1 cross 3 vector, a row vector over here. So this was a column vector. So this E is a vector like this, and this is a 3 cross 3 matrix. So like this. So here we have a 4 cross 3 matrix over here. This is F, our fundamental matrix, and this is I0. That is what we have. So a 3 cross 3 identity and a vector of 0 0 0. Okay, now just multiplying these together, so we get this form, which is again a 4 cross 3, because this is 4 cross 3, this is 3 cross 3. So this is the multiplication will be again 4 cross 3, and when you multiply this with this, you get a 4 cross 4 matrix. So you can see that this matrix over here is almost skew symmetric. You can see that this is 0, this is 0, and there is this thing which also turns out to be 0, because you can see that this is nothing but the epipole. So this is this point over here. So you can see that in the equation for fundamental matrix, there is this epipole sitting over here. So what happens is, when you take a dot product of the epipole with the fundamental matrix, you can see that there will be a triple product kind of a thing that comes over here. So in the triple product, you can see, because this is nothing but a cross product notation. So there is a triple product that is coming because of this. And now you can see that in the triple product there are two things which are same, that is this E dash over here dot product by this E dash. So there are two same terms in a triple product, hence this thing will be 0. So E dash transpose F is a 0 vector, okay, a row vector, because this is ahead, right? So this thing is again 0, hence this is again 0. So what you can see is, this is a skew symmetric matrix, because you can see that this diagonal is 0, and this is again a 3 cross 3 matrix which is skew symmetric. Why is this skew symmetric? Just let's find out. So we had S as skew symmetric, that was our main goal. So S is some skew symmetric matrix. So since S is skew symmetric, it follows this condition. S transpose will be minus S. So this is the basic skew symmetric condition. Now, if you just put this over here, so there is this S transpose, so that will be minus S. And if you take the transpose of this matrix, then it turns out that this will come ahead with a transpose. Then there will be this which will go behind without the transpose, because these both will cut off, and this transpose will also cut off. So you can see the for this matrix, its transpose is nothing but its negative. So by this you can prove that this matrix is a skew symmetric matrix. So this is a skew symmetric matrix, this is 0, so does not matter, and this is also 0. So this matrix that we have got is a skew symmetric matrix. Hence we can say that P and P dash, both of these are one possible solution for this fundamental matrix F. That is a possible camera matrix for this fundamental matrix F. Right. Now there is this thing, what should be a good S? What should I select S to be? So S is just a 3x3 skew symmetric matrix. So it can be any number like this, any matrix like this. So you can represent this S also in a cross product notation like this. So now S is some vector, S1, S2, S3, some 3-dimensional vector, and if you just put this in the cross product notation, you can get a skew symmetric matrix like this. So now you can have any S, you can have any vector S and make its corresponding skew symmetric matrix, but ensure that this condition is satisfied. So whatever S vector you choose, the dot product of that S vector with the epipole should not be 0. This is the only condition that we will have to put on S, that is the skew symmetric matrix, to ensure that P dash is of rank 3. So it is very important that our P dash is of rank 3. So for this to be satisfied, there is this condition on S that S transpose E dash should not be equal to 0. So let us quickly see why this is the case. Why does this condition helps? Let us see that. Okay, so this will need some of the linear algebra basics. So I'll try to explain as simply as possible. So our main idea now is that we have this P dash which is given by SF. So you can see that again. So you have this P dash which is nothing but SF, and the last column is E dash, right? So now I'm just changing this S to the cross product notation, this notation. Okay, so now what I have is, I have P dash as S cross product F, and there is this E dash that is sitting over here. So what I want to prove is that if this condition is true, then E dash that is sitting over here should be linearly independent of the column vectors that this have. So this is actually a 3x3 matrix, so it will have some column vectors like this. So its column vector space, or the column space of this matrix, should not contain E dash. Only then this will be a rank 3 matrix, because this is again a rank 2 matrix, because F is rank 2 and S is also rank 2. So the multiplication of these two matrices will be a rank 2 matrix. So there are only two linearly independent vectors in this matrix, and if E also becomes a linearly independent vector, then only P dash will be a rank 3 matrix. So this is the condition that we have to prove. Okay, so it is a very simple proof. Let us see that. So we have E dash transpose F to be 0. We have seen why. So that means that if E is a vector like this and F is this matrix, so we can say that the dot product of this vector E with the column vectors of F, So the dot product of this vector with this vector with this vector with this is actually 0. So that means that E lies perpendicular to the column space of F. So E is perpendicular to the column space of F, because the column space of F is nothing but a space spanned by vectors in the column vectors, the column vectors of F. So since all the dot products are 0, that means E is somewhere perpendicular to the column space of F. Okay, now since this is not equal to 0, we are putting this constraint that S transpose E is not equal to 0. That means the vector S is not perpendicular to E. Also, that tells you that S is not lying in the column space of F, because the column space of F is perpendicular to E and S is not perpendicular to E. So S cannot lie in the column space. Okay, so S is not lying in the column space of F. That is the first thing that we conclude. Next, now the column space of SXF, that is this notation, is spanned by the cross products of S with the columns of F. So we know that this is nothing but a cross product matrix. So this notation over here basically makes the columns of this matrix to be the cross product of S with the column vectors of F. So the column vectors of this matrix is nothing but cross product of S, this vector, with vectors in this vectors of F, the column vectors of F. So that gives you a column space of SXF, which is nothing but perpendicular to S as well as perpendicular to the column space of F. Why? Because this is the cross product. So cross product gives you vectors that are perpendicular to both of these. So this column space of this matrix will give you a vector which is perpendicular to S as well as perpendicular to this column space that is lying over here. Okay, so now because E is not perpendicular to S, that means E cannot lie in this column space. I hope this is clear. So let us just see it once again. This is the column space of F that is spanned by these vectors that we have. Now, since its dot product is 0, hence E cannot lie in the column space of F. That is the first thing. Next, the column space of this matrix that we have is actually spanned by the column products, is actually spanned by the cross products of S with the columns of F. So the column space of this matrix is nothing but perpendicular to S as well as it is perpendicular to column space of F, because that is the cross product rule. Both the things in the cross product, whatever vector that you get is perpendicular to both of these. So the column vectors that you get by the cross product of S and F will be nothing but perpendicular to S as well as they will be perpendicular to F. Okay, so now since E is not perpendicular to S, that is our condition over here, E is not perpendicular to S, hence E does not lie over here. E cannot be in the column space of this matrix over here. So that proves this, that since E does not lie in this matrix column space, so this is linearly independent to the vectors that are in the column of this matrix. So short proof that this condition is very important to make the P dash a rank 3 matrix. Now, so what can be a good S? So as suggested by this person Long and Weevil, a good choice for S this skew symmetric matrix is nothing but the epipole itself. So you can put this epipole as, so you can just make this e vector as e1, e2, e3. So like this you can make this matrix, and that is a good choice for S, because you can know, you can also verify that E transpose E will never be equal to 0, because this is a non-zero vector. So this dot product with itself will not be 0. So hence this is a good choice for the skew symmetric matrix. So now we have very nicely derived P and P dash, that are the camera matrix, for a fundamental matrix F. So now we know that if we are given a fundamental matrix, we can derive P and P dash with these formulas, which is a possible solution to the fundamental matrix, but it need not be the right solution. It need not be the true solution. It is a possible solution. That's all. So that's all for this video. In the next video, we'll see how can we reconstruct the 3D space from given these camera matrices and the fundamental matrix. So that's what we'll see in the next video. Thank you so much for watching. Thank you.